7 is all about optimization, and that just means that there's all these different choices that we can pick for this certain number, and that choice affects some other value, like say the choice of an angle we pick could produce, the angle at which we throw something could produce different distances, and one of those angles is the best distance, or one of those angles produces the best distance, the farthest distance. So you need to find that angle. Is it 0 degrees, 45 degrees, 60 degrees? What is the best angle to throw this object so that it goes the farthest? It's just an example of an optimization problem. To begin with, let's start with number 1. We'll do number 1 just a little bit differently, knowing that it's an optimization problem. There's these two numbers, and they multiply together to make 110. Or no, they add together to make 110. And so these two numbers that add together to make 110, what's going to be optimum about it is that they also produce the maximum product possible. Right? So we could choose something like 10 and 100. That equals 110. And 100 times 10 is 1,000. Okay, that's pretty big. We could choose 20 and 90, and this would be 110, and multiplying 90 times 20 would be 1,800. So that's even better. So if we just keep choosing numbers randomly, perhaps if we let this next number be a little smaller, like 80, we'll do 80 times 30, see if that works out better. But there's some choice, particularly really for this first number, that's going to be best, because this first number makes this guy be something it has to be the rest of 110. So our choices, one of them is optimal. It's the best one. It produces the greatest product. So in order to do this, of course, we're going to use derivatives and all that sort of thing. So what we need to do is use calculus to solve this problem. What we have is a number plus a number, and together those numbers add to 110. And these numbers multiplied together make some product, like we were just showing examples of. And what we want is this product to be the smallest product possible. Okay. And now at the beginning here, I'll just give you a tip. The tip is the thing that you want to optimize, the product. Optimize, we want to maximize the product. You want to put it in terms of one independent variable of x or y. And there should be, every time you're asked a problem of optimization, there should be a way to do that. In this case, I could take y and write it as 110 minus x. Now I don't have a y anymore because I can just go x times 110 minus x. That makes a product. And as we said before, whatever you choose for that first number, say x, the other one has to be 110 minus x. So now we have 110x minus x squared is equal to p. So, what does this do for us? How do we optimize this problem? Well, all the choices that we make could be mapped out into a graph. We could plug in 10 into this function. Then we do 110, 110 minus the 10, and we get those numbers. We multiply them together. They turn out to make this, and for that particular input, we get 1,000 as the output. And so we would graph all of these, and we should see by this simple example that they would make this parabola, parabola that opens down, right? And for that parabola, let's draw a picture of this parabola. If x were 0, then y would have to be 110, right? Our other choice would have to be 110. But multiplying them together would give us a product of 0, right? And then if our first choice was 110, then the other one would so in the middle here are a bunch of other choices for x, and therefore y, making all sorts of other products. This product's not very big, this one's not very big, but this product right here is the biggest product we can make. It's the well, it's the biggest product and therefore the optimal choice for x. So what we could do in using calculus is find the derivative of this function that produces the parabola, find where the slope is 0, right there, and there's our optimum value of x. So if we take the derivative, we'll have 110 minus 2x equals p prime, right? Because p is changing with respect to x. As x changes, it directly affects p. So dp dx is this function. And if we can find where this function, the derivative, is equal to 0, we find this point at which x is the optimum choice. So we'll put 2x equals 110, and then divide 110 by 2, and x turns out to be 55. If we choose x to be 55, that's the best choice of x. If x is 55, y is 55, so it turns out to be just half of the original sum that we were asked about. So there it is. We found the optimum choice for x. Let's see. Let's try a problem that could be something that happens in real life. Number 20. Ranchers exist and they build fences, so it's feasible that this is a real scenario. So it says that he has 200 feet of fencing, and he's going to make this type of an enclosure where this rectangle is cut directly in half by some fence, so he's using up all his fence for the perimeter and right down the middle. It's already labeled. This is y, this distance, and this guy's x, and this guy is also x. Okay, and cows here, sheep there, I guess. So what would be his choices for x that would, well, x or y, or x and y, that would produce the biggest area, right? He wants to enclose the most animals, or what have you, and so he wants to pick the best choice to put his fence to the best use. So let's write down the things that we know. An equation, I guess, that represents the things that we know. We know that we have 200 feet altogether, and we know that's going to be, well, one of these x's and another, and then 2 more, so 4x plus 3 of these fence lines that are y in length, so 4x plus 3y, right? But now we want to talk about the maximum area, right? Should he make each of these x's 5 feet and make it really long this way? We're going to find out. And to find the area, we would say 2x times y, that's the area of a rectangle, is equal to, well, we're not sure. The area is the thing that's changing, right? It changes with respect to your choices for x and y. Now again, it's best to not have an x and a y, but to have just an x or just a y. So for this problem, we could write that, it doesn't take much calculus skill here to find that x is equal to 200 minus 3y over 4. So now we rewrite this problem in terms of x So 2 times our value for x, 200 minus 3y over 4 times y, and that's equal to a. So let's see, 400 minus 6y over 4 times y is equal to a, and 400y minus 6y squared over 4 is equal to a. Okay. So we can choose lots of different values for y, and those choices are going to affect how much area we get out of that particular corral that we could build for that choice of y. So since we're talking about change, we want to take the derivative of the area with respect to y. So this will be 1/4 times 400 minus 12y. I just pulled that 1/4 out, made that a constant. So a prime equals 100 minus 3y. All right, and so this is the slope of this original function, and wherever this slope is equal to 0, we have found our optimal choice for y. So 3y equals 100, and y equals 100 over 3, which is approximately 33.33. And if y is 100 over 3, then x would be, let's make some room here, well, not much, I guess. 200 would be equal to 4x plus 3 times our choice for y, 100 over 3. So 4x would be equal to 3 times 100 over 3 would be 100, and we subtract 100 from both sides, and then divide, well, so we're going to have 100, and x would be 25. So with x being 25, 25, 25, 25, and then y being 100 over 3, that's our optimal choice for y and for x. Number 23. There's a thing called a Norman window, which can be built by taking this rectangle, right, this is a window that I'm drawing, and attaching a semicircle to the top. So find the dimensions of the Norman window of maximum area if the total perimeter is 16 feet. So the total perimeter, this and this, all added up together is 16, and we want to find the maximum area that we can produce for this window. So what we could do is notice that this is R, right? And perhaps we should go ahead and just write an equation for the perimeter. The perimeter is going to be, well, it's not the whole circle, it's half of the circle, it's a semicircle. So the formula for the circumference of a circle is 2 pi r, so half of that would be pi r. Then we're going to multiply that by these side lengths here. So one of the side lengths we'll call y. Multiply this by y. Alright, we're going to add these together. Okay. So the circumference of half a circle, pi r, plus y plus x. That's the perimeter. Well, let's notice a few things here. First, the perimeter is going to be 16. That's something we were already told. And then we could say pi r times y times, now we could notice that x is is just the full width of the semicircle part, the full width would be 2r. I keep forgetting to write plus here. Plus 2r. And actually we should be adding 2 of these y's. Rolling my eyes at myself for forgetting these things. So the total perimeter is going to be pi times r, that's going to be the circumference of half a circle, plus 2 times y, that's 2 of these vertical sides, and then 2r because it started out as x, and then we notice that x is just the diameter, or 2 times the radius of this semicircle. Alright, but what we're interested in is finding the area and making it the maximum. Alright, so let's write in an equation for the area. Well, the area is just going to be length times width, we could call it width, x times y, plus, well, the area of a circle will be pi r squared, so the area of this half a circle will be pi r squared over 2. Okay. And so now we'd like to express the area in terms of just one variable. So we already see that x is 2r, so that's one thing. And then we'd like to write y in terms of just r, so that we'd have r and r and r. And we could do that with this equation. It would be 16 minus 2r minus pi r, and divide that whole thing by 2, and we've isolated y over there. So this is 16 minus 2r minus pi r over 2 plus pi r squared over 2. So let's see, let's simplify this a little bit. 2r times 16 minus 2r minus pi r plus pi r squared all over 2, because these have common denominators. So let's multiply the 2r through here. We have 32r minus 4r squared minus 2 pi r squared plus pi r squared all over 2. And this is the same as 32r minus 4r squared. And then we have a pi r squared and a minus 2 pi r squared, so together they are just negative pi r squared over 2. So there is the equation for the area, and so what we remember about optimization problems is that our choice of r is going to change the value of the area, and wherever the area levels out, that's, you know, where it peaks out is going to be the optimal choice of r. Wherever that maximum is, that's going to be the optimal choice of r. So we take the derivative, a prime, it's equal to 1/2 times 32 minus 8r minus 2 pi r. We just took the 1/2 out there, took the derivative of 32r, that'd be 32, the derivative of this, okay, there, so on and so forth. And wherever this is equal to 0, we will find our optimal choice of r. 2 pi r. So let's multiply by 2. We'll get 32 minus 8r minus 2 pi r is equal to 0. And 32 is equal to there's radius, so if we remember from our picture, x is just twice the radius.